All right, hello and welcome. Today we're going to be looking at exponential growth and decay. So when we're talking about exponential functions, we're usually going to have equations that look something like this. So it's going to be one number times another number raised to the power of x. So the question is, what do these things represent? So that first number, the a, is going to represent some sort of starting value. The second number, or the base, is going to typically represent some sort of growth factor. And then the x will usually represent something like time. So this is most useful for modeling a lot of real-world situations. So for these, we're going to be dealing with a lot of word problems. So as we read through these problems, we want to label the information that we've been given so that we know how everything gets plugged into the formula. So as I read through the first example, I know that Sarah bought 5 fish. So that's going to be our starting amount. Every month, the number of fish she has doubles. So that is telling us our growth factor. And then finally, we need to figure out how many fish Sarah will have after 4 months. And since our units match, we know we don't need to convert that time. So let's set up our equation. We said that we start with 5 fish. We said that every month, the number of fish doubles. And we're going to let the number of fish grow for 3 months. Sorry, for 4 months. So now all we're going to do is multiply that out. So we said that we want to do 5 fish. We're going to let it double for 4 months. So if I do 5 times 2 to the power of 4, that gives me 80. All right, so for the next one, a piece of equipment costs $50,000 new. So that's going to be our starting value. It depreciates at 15% per year. So depreciates means that our value decreases by 15%. So to figure out my growth factor, I'm going to take 100%, subtract 15%, which is 85%. And since I don't want any percentage signs in my equation, I'm going to divide 85 with 100 to convert it into a decimal. Another way you could have figured that out was to do the decimal conversion first. So I could have taken 15% and written it as 0.15, and instead of 100, I could subtract 1, or from 1. All right, so I know that it depreciates every year, and I want to know the value after 10 years. So again, the units of time match, so I don't need to do any type of conversion. So I'm going to plug in just like we had. So we're going to start with 50,000. Our growth factor is 0.85, and our time is 10 years. So that was 50,000, 0.85 for 10 years. So that's 9,843.72. So once again, that's 9,843.72. All right, so the next thing we're going to look at is what happens when the time units don't match. And so this is commonly used in like finance and like bank accounts and loans and all of that stuff. And so the name for this formula is compound interest. So basically what that means is that you will be given a rate for the full year, but that the interest gets calculated multiple times over that year, therefore changing the percentage and changing the units of time that we need to account for. So that N represents the number of times that we compound each year. So as I'm reading the question, I'm going to treat it just like the ones we had done before. So we need a starting amount. We have an interest rate. So again, we're going to get rid of the percentage by converting that into a decimal. But here's where the extra piece comes in. So this is compounded quarterly, which means we're compounding 4 times per year. So I've got everything except time. And then there it is. So what is our balance after 3 years? All right, so what we're going to do is plug everything in just like we had done before. So I've got my starting amount. According to the formula, I need a 1 plus, then my rate, over my n, and then since I am doing 4 times per year, also need to multiply the years by 4. So the amount I end up with will be equal to this formula. So I've got 500 times 1 plus 0.06 over 4 raised to the 4 times 3 power. So let's go ahead and put that in. So we said 500 times 1 plus 0.06 over 4 raised to the 4 times 3 power. And so as we can see, that's going to come out to $597.81. So again, that's equal to $597.81. All right, let's look at one more. All right, so let's go through and set this up the same way. So notice this time it asks us how much money must be deposited. So we are not given a starting value. But we are given an interest rate, which I'm going to rewrite as 0.09. This interest rate is compounded monthly, which means it's going to be 12 times per year with a final balance of $1,000. So the last thing that we're missing is time, which will be right here. So as I set this up, I don't know my starting value. So I'm going to put a variable in for that. And so if you look at the equation the way they gave it to us, we're going to use P I'm going to plug in my numbers the same way we did last time. And I know that I should equal at the end $1,000. So what I'm going to do is type in everything that I know. So 1 plus 0.09 over 12 raised to the 12 times 3 power. So that's 1.309. So I know that equals to $1,000. So to get my answer, I'm just going to divide 1,000 by 1.309. Therefore, P equals 763.94. That's all we have for today. See you guys next time.